Right now, there's a machine humming quietly in your kitchen. It is probably the most ignored appliance in the house, yet it runs on a technology that is nearly 100 years old. It depends on moving parts that slowly wear out and on chemical gases that can leak into the air over time. In a laboratory in Beijing, a team of scientists has built a different kind of cooling machine. It has almost no moving parts. It uses no traditional compressor and no chemical refrigerant gases. Instead, it uses ordinary magnets and blocks of special metal to pull heat out of the air. If this approach can be scaled up, the refrigerator sitting in your home today could one day look as outdated as an ice delivery truck from the 1920s. This is not science fiction. It is a real advance in physics that could change how we keep food cold, how we cool our homes, and even how we manage heat inside electric car batteries and computer chips. If you enjoy videos that dig into breakthroughs like this, hit the like button. These videos take real effort to research and produce. Subscribe so you do not miss the next one. The idea behind the new machine is surprisingly simple once you hear it, yet it took scientists more than a century to turn it into something practical. Researchers in China appear to have removed a long-standing bottleneck that kept the concept stuck in laboratories. What they built is a fully solid-state cooling device. To understand why your current refrigerator may eventually look old-fashioned, you first need to understand what is actually happening inside it every day. Think about every machine around you that keeps things cold. The fridge in the kitchen, the air conditioner in the window, the cooling system in a car, the freezers at the grocery store, even the units that keep vaccines safe at the pharmacy. Almost all of them run on the same basic idea. It is called vapor compression refrigeration. The method was invented in the 1800s and has dominated cooling for roughly a century with only gradual improvements. It is one of the quietly essential inventions of modern life. Without it, we would struggle with food safety, medicine storage, and livable indoor temperatures in hot climates. Yet almost nobody stops to think about how the system actually works. Here is the process in plain language. The machine takes a special chemical gas and squeezes it into a tight space with a mechanical pump called a compressor. When the gas is compressed, it becomes hot. The machine pushes that hot gas to the coils at the back of the fridge where the heat escapes into the room. Once the gas cools, it turns into a liquid. Then, the machine lets that liquid expand into a larger space. When it expands, it absorbs heat from inside the fridge, making the air cold. The cycle repeats continuously. It is clever engineering, but it brings clear problems. The compressor is a moving mechanical part that pumps up and down constantly. That is the source of the familiar fridge hum. Because the parts move, they wear out over time. That wear is one of the main reasons refrigerators eventually fail. The little compressor runs day and night, using electricity and slowly degrading its own components. It is like a tiny engine working 24 hours a day right next to your food. You rarely notice it, yet it is always there, pushing gas through metal tubes and slowly wearing itself down. The bigger issue is the chemical gas sealed inside the pipes. Those gases can leak slowly over the years. Some of the common refrigerant gases have a very high global warming potential. One widely used gas, often referred to as R134A, can trap heat in the atmosphere more than 1,400 times as effectively as carbon dioxide, according to industry research. Even a small leak from one fridge adds up when you multiply it across every refrigerator, air conditioner, and freezer on the planet. When you consider the millions of new cooling units sold every year, the total amount of these gases becomes enormous. Finding a way to cool without them would make a meaningful difference to greenhouse gas emissions. That is why the search for a better cooling method has become so important. The machine in your kitchen is quiet most of the time, yet it is working hard and slowly wearing itself out. It still relies on a century-old approach that depends on moving parts and chemical gases. This is exactly why a team of physicists in China began looking for a completely different route. They wanted to eliminate the compressor, the moving parts, and the chemical gas. The answer was not going to come from making a slightly better compressor. They had to return to a physics effect discovered in the 1800s. Scientists have known since 1881 that certain materials react in a surprising way to magnets. When you apply a magnetic field to a specific metal, the metal heats up. When you remove the magnetic field, the metal cools down. This is called the magnetocaloric effect. It is a genuine physical phenomenon, and it does not require chemical gases or a traditional compressor. For a long time, the effect was treated as a laboratory curiosity. The temperature change in most everyday metals was far too small to be useful. You could warm a piece of iron a fraction of a degree with a strong magnet, but that was nowhere near enough to freeze water or keep milk cold. The search for better materials took decades. A simple way to picture the effect is to think about a rubber band. If you stretch a rubber band quickly and touch it to your lip, it feels slightly warm. The sudden change in shape creates a little heat. When you let the rubber band snap back, it feels cooler. Certain metal alloys behave in a similar way. except instead of stretching them with your hands, you use a magnetic field to rearrange their atoms. When a strong magnet is brought close, the magnetic field forces the atoms into a more orderly line. That sudden ordering releases heat, and the metal warms up. When the magnet is removed, the atoms return to a more disordered state, and the metal absorbs heat from its surroundings, becoming cold. You can repeat the cycle millions of times. The metal itself does not wear out in the same way a mechanical compressor does. There's no gas to leak and no loud pump. In principle, it is a clean way to create cold. The atoms simply line up and then scatter again, releasing and absorbing heat each time the magnetic field is switched. In 1976, a physicist named G.V. Brown built a working magnetic refrigerator using this idea. He used a rare earth metal called gadolinium. When he brought a strong magnet close, the gadolinium heated up. When he moved this magnet away, it cooled down. The device worked at room temperature and proved the concept was real. Yet for decades afterward, magnetic refrigerators remained bulky laboratory prototypes. They never reached ordinary kitchens. The main obstacle was an engineering bottleneck. Once the metal became cold, you still had to move that cold to the food compartment. In older designs, engineers pumped water or another fluid past the cold metal so the fluid could carry the heat away. The fluid acted as a middleman. Water moves slowly. It takes time to flow, absorb heat, and return. That delay limited how fast the whole cycle could run and wasted some of the cooling effect. The magnetic refrigerator could not compete with a conventional kitchen fridge on speed or power. The fluid itself became the limiting factor. Imagine trying to cool a hot drink by waiting for water to carry the cold to the glass instead of simply putting ice directly into it. The delay makes the whole process less effective. That was the problem holding magnetic cooling back for years. The Chinese team decided the fluid had to go. A group at the Institute of Physics of the Chinese Academy of Sciences in Beijing asked a straightforward question. What if heat moved directly from one solid material to another solid material with no liquid in between? What if the machine contained no fluid at all? Their early conceptual work was published in the journal The Innovation in 2024. The team, including researchers Yuan Lin, Jing Wang, Fengxia Hu, and Baogan Shen, described a hybrid magnetic regenerator. Instead of letting water flow past the magnetic metal, they layered the magnetocaloric material tightly against a different solid that conducts heat extremely well, such as copper or silver. Heat could jump from one solid to the next with almost no delay. There were no pipes, no pumps, and no fluid to slow the process. The design was fully solid state. Because nothing had to wait for liquid to move, the device could cycle much faster. Simulations showed the possibility of higher working frequencies, up to 10 Hz in some models, and strong cooling power per kilogram of material, reaching several kilowatts per kilogram under ideal conditions. A later laboratory demonstration published in the Proceedings of the National Academy of Sciences in 2026 showed a practical solid-state device aimed at thermal management. Even with the imperfections of an early prototype, the device achieved a high heat transfer coefficient of 336 watts per square meter per Kelvin and useful area cooling power through solid-to-solid contact. The absence of fluid also made the structure simpler and potentially scalable for different sizes of target, from small electronic components to larger systems. A fully solid-state design solves several long-standing problems at once. There are no greenhouse refrigerant gases to leak. There is no mechanical compressor to hum or wear out. The machine can be quieter and, in principle, more durable because there are fewer parts that can break. The same basic approach that could one day cool a kitchen refrigerator can also be aimed at very small spots. Modern electronics create intense heat in tiny areas. The chip inside a phone, the battery pack in an electric vehicle, and the servers inside a data center all generate heat that must be removed quickly, or the device fails or becomes less efficient. Traditional cooling often relies on fans that blow dust around and make noise, bulky compressors, or small refrigerant lines that can leak and take up valuable space. A solid-state magnetic cooler can be placed directly against the hot component. Heat is pulled away through solid contact without moving air or liquid. The same technology that keeps milk cold could keep a phone from overheating during heavy use or help an electric car battery stay within its ideal temperature range on a hot day, which can improve both range and battery life. Data centers currently consume large amounts of electricity and water simply to stay cool. Solid-state magnetic systems could reduce both energy use and water consumption. The researchers realized they had not only improved a refrigerator concept, they had created a general tool for managing heat in many different settings, from consumer electronics to large industrial systems and even potential applications in space where moving fluids and mechanical parts are especially problematic. The possibilities extend further. Imagine a medical implant that needs to maintain a precise temperature inside the body. A solid-state cooler with no moving parts and no fluid would never vibrate or risk leaking. Or consider scientific instruments and quantum computing systems that require stable low temperatures. The ability to cool specific spots precisely without bulky infrastructure opens new design options. What began as an attempt to build a better kitchen fridge has grown into a broader approach to thermal management that could touch many areas of technology. Moving from a laboratory prototype to something you can buy in a store is still a long road. The devices built so far are experimental. There is no announced commercial timeline for a household refrigerator based on this exact approach. Magnetic refrigeration as a field still faces real hurdles. The specialized magnetic materials, often based on rare earth elements such as gadolinium, are more expensive than the chemical gases used in ordinary fridges. Mining and processing those materials add cost and raise questions about supply. The strong magnets required to drive the temperature change are also more expensive than a simple compressor. Early systems have sometimes used more electricity than a conventional fridge to achieve the same cooling. The Chinese team removed the fluid bottleneck that limited earlier magnetic designs. Yet manufacturing cost and overall energy efficiency still need to improve before the technology can compete on price with the century-old vapor compression machines that fill every appliance store. If a new fridge costs several times more than a standard one, most families will not buy it. The technology has to make economic sense as well as scientific sense. Factories would need reliable ways to produce the layered solid materials at scale, and the magnets would need to become cheaper and more compact. These are engineering and economic challenges rather than fundamental physics barriers, but they are real and will take time to solve. Every major technology follows a similar path. The first computers filled entire rooms and cost fortunes. Early solar panels were extremely expensive and inefficient by today's standards. Over time, engineers found ways to make them smaller, cheaper, and more practical until they became everyday products. The same process is now underway with solid-state magnetic cooling. The work at the Institute of Physics in Beijing has shown that a fully solid-state magnetocaloric device can function and can deliver useful heat transfer without fluid. Other laboratories around the world are watching and building on those results. Researchers continue to search for better magnetocaloric materials that use less expensive elements while still producing a strong temperature change. They are also refining the solid-to-solid contact methods to reduce any remaining thermal resistance at the interfaces. Progress is incremental, but the direction is clear. One day, the quietest refrigerator in the store may contain no compressor at all. It may simply be a carefully engineered arrangement of metal alloys and magnets that moves heat with almost no moving parts and no chemical gases. The change will not arrive overnight or with dramatic fanfare. It will come in small, unglamorous steps, published in scientific journals years before any product reaches a shelf. Yet the core idea is now proven in laboratory form. A quieter, simpler, and potentially cleaner way of making cold is becoming possible. It is a strange thought that the fridge humming in your kitchen still runs on essentially the same core idea invented in the 1800s. A few laboratories working with magnets and metal alloys may finally be building the replacement. The science is solid. The engineering challenges remain. The economic questions are still open. But for the first time in a long while, the fundamental limits that kept magnetic cooling stuck in the lab have been pushed back. If you found this look at the science behind everyday cooling useful, hit the like button and subscribe so you catch the next deep dive. Turn on notifications if you want to be first to see new videos. Related videos are on the screen if you want to keep watching. Here is a question for the comments. Which everyday machine in your home do you think is next in line to be quietly replaced by something completely different? Let me know what you think.